fundamental idea, the key observation in this business of the crossover between BCS and Bose-Einstein is the observation that, how does this work? Oh, we have to push this button here. Fundamental observation that the BCS wave function, this one up here, this is a many-body, of course, wave function with an indefinite number of particles, contains both limits. Contains also the BCS limit, and that's why it was written for in the first place, but also it contains a Bose-Einstein limit. How you do that? Well, this is the BCS wave function. These are creation operators for fermions with wave vector k and spin projection sigma, and 0 is a vacuum state. Now, by simple algebraic manipulation, you just take this u's coefficient in front, and then you exponentiate what is left by relying on the fact that by Pauli principle, the square of this operator must be 0. So you end up with an exponential of the function, and at this exponent you get an operator which looks like a boson operator, because it creates two fermions as a pair. But just to check whether it is a real operator, bosonic operator or not, we may want to calculate the commutator of this operator here. And you do it exactly, and you discover that this is not a C number. This commutator is not a C number because it contains the remnant of the fermionic operator here. These are the number of operators. So these are natural. The starting problem was a fermionic problem, and you find the fermion nature here already again. However, suppose that for some reason the system you are interested in are living in a subspace of the Hilbert space, where the average number of the fermionic operator here is much less than unity for some reason. Then, for each wave vector in spin projection, you may neglect these two operators with respect to unity, and then this commutator, by appropriate normalization, reduces to the bosonic, the usual bosonic commutator. Therefore, for all practical purposes, the original BCS wave function, if this condition is met, can be written as a coherent bosonic state, which describes the condensate of boson. And of course, this is a broken symmetry state because the average value of this bosonic operator here is non-zero in this particular state. So pictorially, the situation one has in mind is the following, where the two extreme limits are described. Here, this is the occupation number for fermions. This is the wave vector. This is done for each spin component or for the two spin components. There are no magnetic fields included. So you pass from just a Fermi step function at 0 temperature, which is just a stream BCS weak coupling limit, very extreme, no coupling at all. And these are the situations which describe the bosonic condensate, where this occupational number is much less than unit for each vector k. Now, the interesting physics is just in the intermediate situation, when these occupation number crosses over from this extreme fermionic limit to this extreme bosonic limit. You see, in the fermionic limit, the Fermi surface is well identified. In the bosonic limit, of course, there is no remnant of the Fermi surface. To make the ideas more quantitative, what one can do is to take the BCS gap equation at 0 temperature and just rewrite it exactly without doing any approximation in a more meaningful form, which is the following. And here, you see you get the kinetic energy measured with respect to the chemical potential mu, the attractive interaction which is responsible for superconductivity in wave vector space. Now you can define a wave function of psi as a relation of the BCS gap function to the single particle excitation energy. So this is just a definition. And here appears again the average number of the fermionic occupation, which in this theory is written in this form. Now, again, suppose that for some reason the system you're interested in lives in a subportion of the Hilbert space, where this occupation number is much less than unity for all wave vector k, then you can neglect this term here with respect to unity, and then what this BCS gap equation turns out to be is just a Schrödinger equation for the two-body problem with eigenvalue 2 μ equal to the boundary energy of the two-body system. And 2 μ comes from these two, and the μ which is contained in this Xi here. Okay? So what this simple exercise teaches you that in this limit, the chemical potential is renormalized quite strongly, passing from the BCS value, which was just the Fermi energy in the extreme weak coupled limit, to be large and negative in the strong coupled limit. And therefore, one needs to solve the density equation, which relates the density to the chemical potential μ. One has to know the chemical potential with respect to the density, together with the gap equation, the BCS gap equation. Whereas in conventional BCS superconductivity, you just solve the gap equation and know that the chemical potential is spin at the Fermi surface. Now, these ideas were first implemented by Eagles, was the first one to recognize that you had to solve these two equations simultaneously, and that was put on firm ground by Tony Leggett in the 80s, and more recently, I mean 5 years later, was extended to finite temperature by Phil Nozier and the postdoc Schmidt-Mitterling. Now, so let's now implement clearly these ideas, first at 0 temperature and then at finite temperature. So let's consider a crossover problem at 0 temperature. The two-couple equation for the chemical potential, relating the density to the chemical potential, and the gap equation are these two. This is written in a simplified form because, of course, we consider to start at the mean field level. And then we are using the counter potential, which simplifies this writing a lot. And we regularize the temperature short range potential by using the scattering length of the two-body problem, which is here. F stands for fermions. Okay. For this case, there is an exact solution. We found an exact solution at 0 temperature of these two-couple equation in terms of the complete elliptic integrals of the first and second times. And you see, one introduces here a dimensionless parameter, which is the inverse of the product of the scattering length of the two-body problem and the Fermi wave vector, which is a measure of the density of the system. So here you have, again, an example of a collective parameter, a collective coordinates, that drives the system from one limit. When this product is large and negative, you are sure, you're definitely sure that you are in the fermionic limit. When this product is large and positive, you are definitely sure that you are in the bosonic limit. And by changing this parameter, you drive the system from one limit to the other. So what is also a comment I would like to make, then for this simple model one is considering so far, you see you can drive this crossover from one limit to the other either by varying the density, kf, or the interaction among the particles, the scattering length. For more complicated system or more complicated model, you can do the crossover either by varying one or the two physical constant or the other. Now, what happens in practice, if you do the calculation, you discover the crossover region is, when you pass from one, in practice, from one limit to the other, is very much restricted. And this is an example of the calculation of the chemical potential, which, when it's, you see, it passes from being positive to being negative. When it's positive, it's normalized with respect to the Fermi energy, so it reaches the Fermi energy essentially where this parameter here has reached -1, essentially. And then it goes to half the boundary energy of the two-body problem when this parameter has reached +1. So in this narrow range of the parameter, the system is driven from one limit, effectively from one limit to the other. Now, the blue curve are the effect of the fluctuation on top of the mean field calculation, then I will describe shortly. Now, let's pass to the finite temperature problem. Now you still have two couple equations. You include the effective temperature, and in particular, let's look at the critical temperature. So these are the two familiar temperature functions that you should include in the gap function and in the density equation for the density. You can solve not analytically for all coupling, but analytically in the two-string coupling, weak coupling, and strong coupling. And you find that in weak coupling limit, you get the usual BCS expression, where the critical temperature is proportional to the exponent of 1 over the coupling strength. Don't forget that AF is negative in the weak coupling limit. To a strong coupling limit, where a new feature appears, because this critical temperature turns out to be proportional to the Bandy energy of the two-body problem, apart from an entropy factor, which renormalizing in practice by some factor of unity. But what you would have expected, though, that if you, since essentially you get bosonic entities in the strong coupling limit, that this critical temperature would approach the Bose condensation, or the Bose-Einstein condensation temperature, which depends only on the mass and the density of the system. But this is not true. If you solve these two equations, you get instead, in the strong coupling limit, a pair dissociation temperature, which scales like the Bandy energy of the system and not the Bose-Einstein condensation temperature. So what is, how can you heal this feature? Well, let's take back the density equation. In the density equation, you have this Fermi factor, some temperature. You may rewrite it in a fancy way, just an exact way, in terms of the non-interacting Green's, many-body Green's function. I mean, non-interacting functions, which are the building unit of the many-body theory, where this omega s is a fermionic Matsubara frequency. So this is just an identity. But what you can do from this identity here, instead of keeping the non-interacting Green's function, you may add some interaction effects, some fluctuation effects, which are built in this self-energy here, which you see this is essentially a T matrix in the particle-particle channel. So, but it's not a two-body problem, it's a many-body problem, because this is calculated with finite density. So if you do this, if you generalize your equation by introducing this fluctuation propagator here, what you get is the following. Now, if you do not include this fluctuation propagator, the critical temperature, you see, increases without bound. It goes essentially to this two-body bound state energy when you are approaching the strong coupling limit. When you include instead the this fluctuation propagator, this approaches the Bose-Einstein limit temperature rather quickly. Again, the crossover region is rather narrow, from -1 to +1. So let me summarize this by just saying, again, if you include only the non-interacting Green's function density equation, you get the temperature that you get has a meaning of the pair dissociation temperature. If you instead include fluctuation, you get what you would expect, the Bose-Einstein condensation temperature. And of course, the interest in physics comes about when the two temperatures are of the same order, whereas, for instance, in helium-4, the two temperatures are widely separated. The superfluid temperature is about 2 Kelvin, whereas the pair dissociation temperature is about the temperature associated to 60 electron volt. Now, let's see how this can be relevant for the Couperin superconductor. Well, this is just a shortcut version of the phase diagram of this high-temperature superconductor for essentially this bismuth-based compound. It's only part of the phase diagram. This is temperature versus doping. The stoichiometry composition of the system is an antiferromagnetic compound, and the antiferromagnetic phase is not shown here because of its no relevance what you are going to say. This is the superconducting critical temperature. The system is at optimal doping, where the temperature is the highest, is in the underdoped region here and the overdoped region here. And what is interesting then, in this system, you get a new phase here, which is called a pseudo-gap phase, where you identify crossover temperature. This is a sharply identified temperature which is associated with phase transition to superconducting system, whereas this is a less defined temperature. You see this is a shady area, and these error bars are larger because this is really a crossover temperature. What happened there? What happened is the following, that below this temperature T star, you get a pseudo-gap in the system. In other words, the density state is depressed, is strongly depressed. It's not zero, but strongly depressed. Both in when you measure spin property, like in the magnetic susceptibility, or when you measure charge property, like in angular resolved photoemission experiment, or in tunneling experiment. You see a strong depression of the density state. And also when people measure that the most physical property, of course not the mass of the pair, because they would not be relevant, as smoothly evolved with the system becomes superconductor across TC. Now, within this sort of crossover approach that I was describing, the pseudo-gap is understood has a precursor of superconductivity, because you get strong pairing not only below TC but also above TC in this new phase that I was describing. And essentially at T star, incoherent pairs or almost bound pairs start to form, and you identify therefore T star with a pair temperature, whereas at TC, the coherence among these pairs is established. Unfortunately, the physics of the group rate is complicated by several features. The degrees or number of degrees of freedom is very large. First of all, the gap parameter has D-wave symmetry, it's not S-wave symmetry. You get lattice effect, like mass structure represent one over singularity in the density state and so forth. The origin of pairing is unknown, but is not of concern to us. And then you get additional effect, like the mode transition, localization transition in the low doping region. You get antiferromagnetism organized in stripes, and charge also organized in stripes. So you get a really lot of degrees of freedom which can obscure the physics which is behind. Well, probably magnetic field can help understanding the origin of this phase, the pseudo-gap phase. And experiments done up to 20 Tesla have essentially obtained this result. Then T stars depends weakly on age, where the system is in the underdoped region up to optimal doping essentially, whereas depends strongly on age for overdoped region, and whereas the critical temperature TC always depends strongly on the magnetic field. For these two different results, one is tempting to conclude that the two temperatures have different physical origin. However, there have been recently some measurement by Shibauchi et al. Who apply pulse field up to 60 Tesla and then extrapolate the result essentially to 100 Tesla for several doping values, have systematically determined what they call a pseudo-gap critical field, above which the pseudo-gap phase is destroyed at any temperature. This picture is taken from the paper, experimental picture. Again, you see these two, this is a critical temperature, this will be this T star temperature merging together in the overdoped region. But what is relevant is this inset here, where this pseudo-gap critical field is related to the T star S0 field. And you see a sort of linear behavior. Of course, you have to add this point here to go to experiment and theory. And they had identified this simple experimental relation, sort of Zeeman-like relation, where the critical temperature S0 field is connected with the pseudo-gap critical field, and it really looks like that the spin degrees of freedom are the most relevant in this region. How much, Madame, do you have? 5 minutes. Now we have done quickly we have an explanation for this. Paper is just appearing in fifth or letter. The model is simple. This is this system of anisotropic layer structure. We embed this fermion in an anisotropic lattice. and the attraction is between electrons in plane, and you get a band structure where you get Hoppe matrix element both in plane and out of plane. And of course, you include the effect of the magnetic field to the spin degrees of freedom. You still have two coupled equations to be solved, but now you have two new features, the d-wave symmetry of the gap and the presence of a magnetic field to this spin degrees of freedom here. Now, we solve, of course, we don't know what this number is, so we take it from an experiment by identifying the temperature, the critical temperature, this T-star temperature as zero field with experimental value. But this is the only information that we take from experiment. Then we solve the two equations for the unknown T-star and the chemical potential for given sample, so for given value of the density and of this coupling, for several values of the field. A typical curve that you obtain is the following. So these are the theoretical values, and that is a polynomial interpolation to the value. And from this we extrapolate and we can locate, we can identify this critical field here. We do it for several samples, and the curve that you obtain is the following. Again, these are the experimental value, and with a line which of course has to cross zero here. These are the theoretical values. There is a factor of 2 essentially in the slope of this curve. We get a linear coefficient. We don't get the slope on one, but we have an explanation for this difference, which is essentially related to the factor, to this entropy factor, log factor I was showing before. Now, very briefly, let me mention another very exciting system where these ideas can be applied, and we are pushing on experimentalists on doing this experiment. There's been an experimental breakthrough recently by a German group led by Klaus von Klissen in Stuttgart, who may make this experiment possible. So these are electron hole double layers. You have a sandwich of gallium arsenide and gallium aluminum arsenide in between. And the key words in this business is the exciton condensation in a semiconductor. The situation is a very simplified sketch. What the situation has, you have gallium arsenide on both sides, gallium aluminum arsenide in between. You create, by some gate voltage, an excess of electron on one side and an excess of holes on one side, and of course the Coulomb interaction will bound these pairs in exciton, and you may get the excitonic condensation. Now, the interaction is provided by the Coulomb attraction, which is fine. There is no way to modify the distance, essentially. I mean, it's very hard to modify the distance between these two planes to modify the Coulomb interaction. So the way to drive the crossover is to vary the density of the system. Just one minute. To vary density. So what we are doing in collaboration with David Nilsson, University of New South Wales in Sydney, where I spent some time before coming here, you drive the crossover by varying the density, and then you may make by apply different gate voltage to the two sides of the sandwich. You may do a density imbalance, which will act effectively on this system as a magnetic field, and therefore can help you in identify which side of the crossover you are in. Just a very last sketch. Of course, it would be nice to talk with the expert here, because we're also trying to convince experimentalists in Florence to do this experiment on the Bose-Einstein condensation of Fermi atoms. Because this will be really the ideal system to look at this crossover from BCS to Bose-Einstein, because there are no other degrees of freedom to be considered, to be worried about. So the system is dilute, is embedded in the continuum, there is no lattice effect, the system is neutral, so there is no Coulomb interaction to be worried about, and we have a theory which controls the transition from a dilute interacting system of Fermi on the one hand, and elute interactive system both on the one hand, and how can you bridge the two. And of course, since you cannot vary the density, the only way to make this crosswave could be to exploit the presence of Feshbach resonances. There may be two different experimental ways to do it, either by sympathetic cooling, which has been also realized, or using different internal state, like in the genes group has been doing. And also, I would like to mention this recent experiment done with boson, where you pair. You can make these pairs, but with boson, not with fermions, but this can be probably extended to fermions. So thank you for your attention.
For questions?